We constantly guess what the future will look like, but we rarely ask how it will be funded. Let's run the numbers. Specifically, we must evaluate the economics of localized weather modification. If we assume that weather modification technology becomes technically viable and cheap to run, we might expect it to solve agricultural water scarcity. However, this expectation ignores resource allocation constraints. Under this assumption, controlling rainfall in one area means altering the atmospheric water flow. The atmosphere is a shared resource, and this localized control inherently impacts neighboring regions. This creates a major transboundary coordination problem. Because the moving atmosphere has no physical borders, one region's induced rain is effectively subtracted from another region's potential supply over time. We must analyze how economic incentives align when a resource is non-excludable yet highly rivalrous. The technology could shift rainfall, but it cannot create new water out of nothing. So, who pays for the weather and who captures the value? The fundamental economic mystery lies in the non-excludable nature of the sky, which resists traditional private property rights. As localized weather systems are manipulated, we identify the binding scarcity. The bottleneck is not the mechanical cost of seeding clouds, but the finite volume of atmospheric moisture. When one territory unilaterally induces rainfall, it creates a negative externality by reducing the downwind moisture. This strategic action is rivalrous because the water can only fall once. Here is the constraint: there is no mechanism to prevent downwind neighbors from experiencing artificial drought. The atmosphere remains non-excludable, meaning anyone can access it but none can own it. The observable consequence is a geopolitical coordination failure. Without property rights, nations have a strong incentive to capture rain before it crosses their borders, leading to severe depletion. It comes down to scarcity. If rain becomes a contested asset, regions will invest in technology to intercept clouds, creating an inefficient and costly weather interception arms race. This regional rivalry threatens to turn the sky into a zone of strategic resource grabbing. The stakes are not just local water security, but the stability of the global commons. To analyze this scenario, we must define public goods. A pure public good is both non-excludable and non-rivalrous, meaning one person's consumption does not reduce another person's utilities. However, the atmosphere represents a common pool resource. It is non-excludable because we cannot stop anyone from breathing or modifying it. But its moisture content is always highly rivalrous. When a resource has these conflicting characteristics, it is vulnerable to the tragedy of the commons. Each actor consumes or alters the resource to maximize private benefit, ignoring social costs. Interestingly, we can compare this to historical river-sharing conflicts. When an upstream country builds a dam, it reduces water flow to downstream nations, creating severe and lasting geopolitical tensions. The key difference is that atmospheric moisture moves in complex, less predictable patterns. This complexity makes tracking the origin and destination of diverted rainfall exceptionally difficult for global regulators. Without clear measurement, enforcing water rights becomes nearly impossible. We cannot easily prove whose rain was intercepted, leaving neighboring states with little recourse but to retaliate directly against neighbors. This lack of excludability creates a classic free rider problem. Some regions might benefit from the weather modification efforts of their neighbors without contributing to the operational costs of the program. Consequently, private markets would tend to underprovide weather stability. The funding model decides what survives, and without state coordination, this unified global atmospheric management remains completely financially unsustainable. The core mechanism of this conflict begins with unilateral weather intervention. A single state decides to seed clouds to alleviate a localized drought within its own domestic agricultural territory. This action alters the dew point and triggers precipitation earlier than would naturally occur. The immediate result is localized water abundance, satisfying the initiating state's domestic agricultural needs. However, this localized precipitation depletes the humidity of the moving air mass. As the wind carries the air mass downwind, it contains significantly less moisture to support natural rainfall. Follow the incentive structure. Seeing their rainfall decrease, downwind neighbors are incentivized to deploy their own weather modification systems to capture whatever moisture still remains in the passing clouds. This creates a sequential chain of interception. Each state along the wind path extracts water, leaving the final regions in the sequence with severely depleted atmospheric moisture resources. The pricing of water under this scenario becomes highly distorted. Because there is no market for clouds, the price is set by the capital cost of the interception technology. This technology-based pricing excludes the negative externalities imposed on downwind neighbors. The social cost of the diverted rain is completely unpriced, leading to rapid over-extraction by early actors. Now, as the externality grows, it triggers institutional friction. States may attempt to negotiate treaties, but the high cost of monitoring atmospheric moisture prevents stable agreements from forming. Without enforceable treaties, states face a classic prisoner's dilemma. Even if cooperation is mutually beneficial, the dominant individual strategy is to intercept rain before others can take it. This competitive dynamic leads to an inefficient Nash equilibrium. Every state spends capital on weather modification, but the total amount of available water remains unchanged, wasting valuable economic resources. Furthermore, the distribution of water becomes highly unequal. Wealthy nations with superior technology can capture a disproportionate share of moisture, leaving poorer regions with severe and artificial droughts. This distributional conflict shifts the focus from agricultural production to technological capability. The economic returns depend on possessing the most powerful and advanced atmospheric manipulation systems in the region. The resulting resource insecurity discourages long-term agricultural investment. Farmers cannot predict rainfall when neighbors can redirect it, causing crop yields to fluctuate and food prices to rise sharply. In response, some states may deploy retaliatory weather systems. For example, they could seed clouds early to induce hail, destroying crops in the initiating state as a strong deterrent. This escalation highlights the fundamental failure of localized management. The atmosphere behaves as a single integrated system, but the decision-making remains highly fragmented and competitive among rival states. To evaluate this model, we must establish its boundaries. Under this assumption, weather modification is only rivalrous when atmospheric moisture is already the binding constraint for overall agricultural production. For instance, in regions with abundant natural rainfall or access to desalinized ocean water, weather manipulation would not create significant externalities. The conflict depends entirely on localized scarcity. Additionally, an alternative equilibrium could emerge if states establish a centralized global weather authority. Under this cooperative structure, weather modification would be funded and managed in a cooperative manner. However, this cooperative model assumes that nations can agree on how to distribute the rain. In practice, negotiating water distribution across borders remains a major and difficult diplomatic obstacle. We must also note the physical limitations of this technology. Weather modification cannot generate new moisture. It only changes where and when existing atmospheric water falls to the ground. This physical boundary means the total global supply remains fixed. In conceptual models where water is scarce, unilateral diversion always imposes an equal and uncompensated cost somewhere downwind. A validating case is found in transboundary river basin disputes. When upstream nations divert water, downstream nations consistently suffer, demonstrating the predictable and structural conflict over shared resources. This brings us back to the primary question of who gets the rain. The answer is that without property rights, the most technologically advanced nation captures the water. The consequences of this unregulated capture are clear. It shifts water scarcity from a natural challenge to a geopolitical conflict, increasing the overall volatility of regional agricultural commodity markets. Change the assumption, change the equilibrium. If we introduce enforceable global weather permits, we could theoretically allocate rain rights to prevent this unilateral interception of agricultural cloud systems. Under this assumption, states would have to purchase permits to modify the weather. This pricing mechanism would force them to internalize the negative costs imposed on downwind neighbors. However, implementing such a permit system requires high monitoring precision. We would need to verify exactly how much moisture a state extracted from a moving air mass over time. Until that technology exists, the permit market remains a theoretical concept. The practical resolution is that weather modification will continue to drive geopolitical conflict rather than global cooperation. This reality forces us to reevaluate the promise of weather control. The technology does not eliminate scarcity. It merely relocates the tragedy of the commons to the atmosphere. By recognizing this bottleneck, we can avoid the mistake of funding unilateral projects. True progress requires building the institutions to manage the sky before we deploy the technology. Ultimately, the atmosphere remains a shared public resource. Any attempt to privatize or control it unilaterally will tend to trigger defensive and highly retaliatory responses from neighboring states. In practice, when evaluating futuristic water solutions, we must look beyond technical feasibility. We must inspect the institutional framework that will govern resource allocation and resolve conflicts. If a project lacks a clear mechanism for resolving transboundary externalities, it is likely to trigger geopolitical conflict, regardless of how efficient the underlying technology is. We should analyze weather modification proposals by testing who pays and who captures the value. If the benefits are private but the costs are public, failure is likely. Another application is to design robust verification systems. Developing methods to track atmospheric moisture flows is a necessary precursor to any stable and lasting international weather treaty. Furthermore, we must compare centralized funding models with competitive ones. Cooperative international funding tends to produce more stable and equitable resource distribution outcomes than unilateral spending. We must also maintain a clear distinction between a thought experiment and a forecast. This analysis helps us map the incentives, not predict a specific geopolitical future. By focusing on scarcity sets the price, we can better evaluate the true cost of these technologies, including the hidden geopolitical risks they introduce. The critical step is to design institutions that align individual incentives with global resource stability. Only then can we hope to manage the global commons effectively and peacefully. When we analyze weather control through the lens of public goods, we see that the physical technology cannot solve the economic bottleneck. The future is just incentives at scale. See you tomorrow.